Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leader series, addressing Harmonics issues of grids with high penetration of grid-connected power converters, calibration and measurement. My name is Megan Purdy and I'm from Engineers Australia. Firstly, in keeping with our customs, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. Before we get started today, I would like to acknowledge that our webinar has been hosted with Engineers Australia's industry partner, Queensland University of Technology. QUT is a major Australian university with a global reputation and a real-world focus. Its courses equip the students and graduates with the skills they need for the world of today and tomorrow. They are an ambitious institution with a rapidly growing research output focused on technology and innovation. The Times Higher Education 2020 ranked QUT in the top 180 universities in the world and the best young university in Australia. Their strategic plan, Blueprint 6, establishes QUT as a university for the real world and charts its provision of transformative education and research that is relevant to our communities. With approximately 50,000 students, QUT places a premium on the national and international accreditation of all professional degrees. Well known for their strong links to industry and government, the high impact of their research, which involves multidisciplinary teams, can be seen across areas as diverse as climate change mitigation, digital media, materials science, and biomedical innovation. I would now like to welcome our moderator for today, Kate Summers. Kate is an experienced power and control engineer with over 25 years of electrical, market and regulatory experience and was awarded the National Professional Electrical Engineer of the Year 2020. Kate has provided technical leadership for the wind industry in NER working groups, has been the chair of the Grid Directorate of the CEC and is a current board member of Engineers Australia's Electrical College. As a principal consultant with Ikistica, Kate is developing and strengthening remote and regional Australia's capability to deliver reliable power solutions in the renewable energy sector. Please join me in welcoming Kate Summers.
Thank you, Megan, and welcome again to our viewers. I'm Kate Summers. I'm a principal consultant with Ikistica in power systems engineering. I'm also a national member of the Electricity College Board in Engineers Australia. I'm a power systems engineer with over 28 years experience in the industry across all facets, including the electricity market. I'd like to welcome our first speaker, Professor Firuz Zare. Professor Zare is head of School of Electrical Engineering and Robotics at QUT. He has spent over 20 years in academia, industry and international standardisation committees as a leader, project manager and senior specialist. Professor Zare has significant experience in team building, management and leadership across multidisciplinary emerging research and teaching activities in cross-sectional research, technology projects, national and international standardisation committees. He has been collaborating with several international research centres and industries in Australia, Europe, USA and Japan in the fields of energy conversion systems and nanosecond pulsed power technology. Please welcome Professor Firuz Zare.
Thanks for the introduction. Good afternoon, everyone, and welcome to my presentation. I'm Firuz Zare, head of the School of Electrical Engineering and Robotics, and today I'm going to talk about the harmonic issues of grid-connected inverters in distribution network. Together with my colleague, we're going to focus on calibration and measurement. Before I start the technical content of high-frequency harmonics in the network, I would like to explain definition of harmonics and interharmonics in power system. So if you look at this simple example, you can see that we have fundamental frequency, which is 50 Hertz or 60 Hertz, depending on the network. And in this specific case, we have harmonics, fifth harmonic, which is the integer number of the fundamental frequency. and we have interharmonic, which is non-integer frequency of the grid, and basically according to IEC and IEEE standardization, harmonics are defined up to order of 40th based on IEC or 50th based on IEEE. But recently we have received lots of complaints in terms of harmonic issues at high frequency. So therefore, according to IEC, harmonics are defined below 9 kilohertz. And there are different measurement methods based on grouping that I will explain later during my presentation. So there are different standards in network to make sure that the quality of the network can be controlled. So when we are talking about harmonics below 2 kilohertz, we have several standards and regulations that we can work on it. So 3-16, IEC 61003-16 is one of the new standards that I'm the task force leader, and this is specifically for grid-connected renewable energy systems. But the other standards for harmonics are for low power or high power. Having said that, the existing gap is based on 250 kilohertz and has been split into two different frequency range of 2 to 9 kilohertz for harmonic emission, mainly for some of the equipment that we expect can generate significant harmonics into the distribution network, and higher frequency 9 to 150 kilohertz, mainly localized based on immunity issue, but these are covered by CISPR. So we will explain how different technologies can affect those frequency ranges. So recently, we know that there are different enabling technologies based on power electronic can basically improve the efficiency of the system and also utilize renewable energy conversion from solar or wind into the electricity in distribution network. So these devices are based on switching devices like IGBTs or MOSFET, which can generate harmonics in the network. Some of the motor drives in residential or commercial or industrial networks are based on either diode rectifier or different types of power electronic systems, but these generate different harmonics, and I classify them into different types. The type 1, in fact, is based on the diode rectifier. It can be for single phase or three phase, and because it's very reliable and cost effective, still we have lots of products in the network. Type 2 is a very special network type of single phase device, and the current waveform is almost sinusoidal with some high frequency harmonics at switching frequency of the system, and normally the switching frequency is around 30 kilohertz. Type 3 and 4 are for low power, high power grid connected inverters based on bridge rectifier, and normally switching pattern are above 2 kilohertz. So when we look at type 1, so this is a very well-known type of topologies that diode rectifier either for single phase or three phase are used, and the cost is very low, so that's why it's still utilized in many products. But for single phase or three phase, these devices generate significant low order harmonics, means below 2 kilohertz. So that's why we put and design different passive filters to make sure that harmonic mitigation at device level can be managed and controlled. So having said that, we have different standards, and I'm just trying to highlight one of the standards, 61003-12, which is for three-phase, high power, and we have different relaxation to decrease or control the harmonic in the network because of the cancellation. So therefore, you see that under different conditions based on the grid impedance, based on the type of transformer, short circuit ratio, the device can generate different harmonics in the network. But the other factor which is important to discuss is that even with the diode rectifier that you can see here, there are different types of passive filters for each product that we might have for these type of converters. For example, one of the sectors that you can see here doesn't have any inductors in the filtering system. The other one has a DC filter, DC inductor filter, and the other one has the AC inductor. And each type of filter has pros and cons, but in a production line, when we have different products from different manufacturers, because of their design and filters, we might have different resonances in that private network affecting quality of the system. So therefore, device analysis is one aspect of the harmonic control, and system is the most challenging to make sure that all aspects of the design and system parameters can be considered. So from utility point of view, medium voltage, power quality of the voltage at medium voltage is important. So because of combination of commercial, residential, and industrial sectors, some of the single phase units, power converters, with a different phase angle of their harmonics can cancel three-phase devices with almost opposite phase angles. So that's why we are expecting that harmonic cancellation can happen in the network, especially in medium voltage. So that's one of the reasons that we have different types of regulations and standards for grid-connected inverters. So if we review this diagram, so I'm going to focus now on type 2, 3, and 4 types of power electronic systems generating harmonics above 2 kilohertz. And I'm going to focus on each topology and how high order harmonics can be generated. Type 2, in fact, is based on diode rectifier, as you can see, but we have one switching device, which is high frequency switching device. And this switching device is basically controlled based on a specific circuit, which is in fact based on a control system. And if you look at the blue line, that current waveform, this current waveform is in phase with the voltage waveform and is very close to sinusoidal plus some harmonics. And those harmonics are high frequency. So one of the advantages that although this system is unidirectional, which means that the power basically flows from grid to the device, and in that case, normally up to 5 kilowatts or slightly higher can be used for different products, either for motor drives or battery chargers or different systems. But having said that, this is the advantages that we can improve the quality of the current waveform. But the switching frequency that normally is designed in many products is at around 30 kilohertz. So that system can improve the quality of harmonics at low frequency, below 2 kilohertz, but definitely create some harmonics at high frequency. And if we expect these devices are utilized in residential appliances or home appliances, then we are expecting that in residential network we have higher frequency around that frequency range. The other types, type 3 and 4, are based on active in-feed converter technology, which is bridge inverter, either single phase or three phase, is a combination of LCL filter, and it has to be LCL filter to make sure that ripple high frequency harmonics can be controlled. And the main advantage of this topology is bidirectional power flow, which means that it can be utilized for battery chargers, renewable energy, or different systems that the power can be generated to the grid or back to the device depending on the system. For example, in battery charger, if you want to charge the battery, we take the power from grid And if you want to feed back, we can transfer the power from battery to the network. So why this technology is so critical? This technology is so critical because there are many design factors which can be different from one product to another product. For example, LCL filter is significantly important for this design to make sure that the switching pattern, the voltage stress coming from that inverter can be mitigated at the grid side, left side, to make sure that voltage stress is minimized as well as the current waveform can be sinusoidal. So we have IEEE 1547 focusing on some of the active in-field converters, and I'm the task force leader to finalize IEC 61003-16. We have already finalized the document. We are expecting that next year that will be approved by the International Standardization IEC. And that will be a big step. The other factor is switching frequency, which is important in terms of design factor. And it can be different starting from 2 kilohertz up to 9 kilohertz for very high power, or starting from 20 kilohertz to even 100 kilohertz for low power that we have seen some products. And the challenge is that when the power is increased, frequency is decreased to manage the losses. And pulse width modulation or control methods are completely different depending on how you design your system. But I have to say that generally speaking, the filter is based on LCL filter. There might be some LC filter for grid forming and grid following type of system, but let's focus on LCL filter design and type, which is very common in almost many products. So quality and performance of active in-field at system level is under question, and we have seen lots of issues in the network. And the main reason is that we can see lots of resonances, and these devices together with grid impedance can create some resonances that we're going to study. So let's start with this slide, which is in fact one of the measurements that I did in residential area in Queensland. And you see that the harmonic frequency, or this is the maximum value. We have done lots of analysis. I just want to highlight that even the maximum value, depending on the measurement, it shows that sometimes high frequency below 50 kilohertz can be significant. But having said that, this is one of the reasons that we want to highlight that harmonics in the network at high frequency, it's very diverse and depending on how these devices interact together. Based on the collaboration that we had with different standardization committees and also with manufacturers and some companies, we have realized that have been lots of reports regarding communication and signaling errors for some of the equipment in distribution networks like ripple control signal and PLC, especially in Europe, because of the frequency below 150 kilohertz. And some of the measuring devices like smart meters, we have seen some reports in terms of wrong measurement or significant errors in the measurement. And we have also seen some resonances in low voltage, medium voltage, tripping the network and tripping solar inverters, especially in residential area or wind farm. And I have seen severe resonances and failure in cables of wind farm and some reports for the transformer and many other sensitive devices because of high frequency that I have reports from my colleagues and from industry that I'm allowed to share those ones in the next slides. So when we are talking about high frequency harmonic issues, in fact, we are talking about short-term resonances or transient. We are talking about immunity or lifetime issues that two devices can interact together. And the other one is the steady state high frequency harmonics. It can be for hours or it can be for minutes. So the main reason that we have some of the high frequency harmonic emissions in the networks are because of the power electronic topologies and control systems, which are completely diverse. And I have explained 4 types of power electronic systems. And also we have grid parameters like background voltage harmonics, unbalance, grid impedance, and weak grids. All can affect the quality of the network and grid connected inverters. And the other one is that when in industrial networks, for example, if you have high number of motor drives or grid connected inverters, they interact with each other, and we have seen some resonances and harmonic issues at device and system level. This is one example that one of my colleagues from distribution network in Germany, they reported that the traffic light was disturbed because of high frequency harmonics generated by one of the devices, and they have realized that the control system was affected and the traffic light didn't work for hours. And that's one of the reasons that they realized that the resonance frequency of the control system was tuned at the harmonic frequency of the other device. This is another example that AEBLA, one of the power quality manufacturers, reported that when 2 battery chargers, electric cars, connected at the same point of common coupling, they have seen some immunity and resonances affecting each other. For example, when electric car A is connected to the network without any other electric car connected, so you can see the red waveform, which is very sinusoidal in phase with the blue one, and that shows the quality of the charging system. But the moment that electric car B is connected, the current waveform of the A has been affected. Looks like that the switching frequency of the charger B was at the resonance frequency of the A, and that's because there are 2 different types of charging devices. So that's why, as I explained, when we have grid-connected inverters with different topologies, different controls, different filtering, so resonances, switching frequency can be different and the system can interact with each other. So here we see the transient and resonances, which is more or less immunity issue, and sometimes harmonic can be propagated to the distribution network depending on the frequency and amplitude. This is one of the reports by Sigre, and again I want to emphasize that here we are talking about 10-12 cycles that the grid-connected inverter has been affected and then switch off. So when you're talking about high-frequency resonances or harmonics, we are not talking about the conventional harmonic analysis that we can measure, for example, for a day, and the performance is more or less same. No, you can see that the solar inverter works very well, but only within 10 cycles, less than 1 second, suddenly some resonances can happen and the system can basically be affected. So again, this is transient and short-term resonances which is happening and tripping the solar inverter. This is the other example being reported by AEBLA, and they reported that the alignment control, which is based on power electronic motor drive, connected to more or less same point of common coupling that solar inverters are connected, and they have realized that the control system was affected because of this high frequency. If you see that red area, that is the high frequency content of the harmonics affected the control system. So when you have different high frequency power electronic systems connected together, apart from harmonic generated by the device propagated to the network, they can interact with each other, and depending on their internal impedances, current harmonic can be circulated through another device affecting their control system. So again, this is transient and short-term resonances with immunity issues. So this is another example for power quality measurement that we did in Australia, and you see that the grid-connected solar inverter should have more or less perfect sinusoidal current waveform, but you see depending on the different operating modes, the current is not sinusoidal, purely sinusoidal, it has significant harmonics in the network. Just to focus on that specific case, if you look at this measurement, each pulse sector on the right-hand side, this blue diagram, it shows basically 1 day measurement. So when the current is 0 means during the night, solar inverter is switched off, and the other one during the day. So that specific frequency, 2.9 kilohertz, looks like very stable for a couple of days, except 3rd of February, you see that significant resonances happens for a few hours. So that's a short-term resonance or harmonic issues that can trip the network or can affect the transformer or can affect the cable or many other devices in the network. So if you look at the current waveform for that specific frequency around 3 kilohertz, the amplitude is significant, over 140 amps, and that is something happening in short term. So if you do measurement today, and if the current is very low, for example, 5 amps or 10 amps in this example, that doesn't mean that this is the quality of the solar inverter happening every day, every hour. No, it can happen depending on the transient large signal disturbances coming that the control system of the inverter cannot handle it. So we have done lots of analysis. So we have developed very smart and interactive system and software which can analyze harmonics from the measurement from the field, and that has been one of the tools that we have implemented to analyze harmonics. The other tools, simulation tools that we have developed for large scale power electronic systems connected to different feeders, transformer. So in that case, we are able to analyze different conditions, different power level, different topologies, different transformer, and different length of the feeder and cable in which to estimate what is happening when these converters are connected to the network. And that simulation basically helps a lot to understand how those factors should be optimized for a specific system. And we have also done lots of analysis for grid-connected inverters. We are aware of the complex and nonlinear behavior of the inverters at the system level. So therefore, when these are happening, in fact, the background voltage harmonics can affect the current quality. And we have realized that this analysis can increase or decrease the current harmonic from each device. We have published several papers to demonstrate the nonlinearity of the system, and that's why this is important to identify that when you buy power electronic device, that device is tested at the device level under more or less sinusoidal conditions. But when those devices are connected to the distorted grid, so we expect much more harmonic coming from those devices depending on the background harmonics. So I want to clarify that the system analysis is completely different than device level. So that's why the harmonic and interaction in the network will be different. We have also done different resonances from different feeders, especially with long cables utilized in distribution network or wind farm. And when these devices are connected to those, our electronic devices connected to those cables or feeders, we expect some significant resonances because of the harmonics and because of those resonances. And these are our simulation results. And we have also model transformers and the Miller effect of the transformer. If you can see ZA, it can be capacitive coupling between turns of the transformer of primary and secondary, and we have analyzed that this capacitive coupling can be a few nanofarad. And if you have some switching pattern coming from the distribution network or from solar farm on and off, that can affect the transformer, can affect the cable because of those LC effect of the cable and transformer and overshoot coming from those switching transient. This is very interesting test result that we did in a network. So this is a solar farm connected to one residential area. So if you look at the blue line, you see that the harmonics coming from solar inverter is not passed through the transformer to the grid. It's circulated to the residential area, and that's the main reason that in residential area we have lots of capacitive filtering in home appliances or in a different filters, different equipment. So that's why capacitor means low impedance at high frequency, which can create some immunity issue. This is one of the analysis that we did for solar inverters in terms of modeling. So when we do LCL filter, when we have different passive damping with the resistor or the LCL filter, and when we design the controller GC here in this block diagram, overall we can simplify solar inverter as a current source, generating fundamental and harmonic depending on the transfer function of the AS. But the most important factor is that this current source is not an ideal current source, has an input impedance, and the input impedance depends on many factors: control system, control parameters, and your LCL filter. And it has some resonances. And those resonances in that solar farm basically can interact with some other inverters. And this technology is similar to the battery charger, which means that all battery chargers based on active in feed converter, they have some resonances. And this is, in fact, is the multi-inverters connected together. And in that case, when we have all technologies similar to each other, in this case, we don't have any problem in terms of resonances because they are more or less same technology. But if you look at residential area where we have high number of different solar inverters, we expect significant interaction between some of those ones if the switching frequency of one of those is tuned at the other impedance of the other inverter. So that's why we expect some interaction in residential or in grid-connected inverters. So I'm going to finalize my presentations and also the conclusions in terms of high-frequency harmonics in the network. So based on the reports, analysis, measurement, and the working group in standardization, the high-frequency can affect the quality and stability of the grid because of the tripping, because of those failures. And harmonics in the network, especially high frequency, it is not the steady state for hours. It can be some severe transient or short term within second or minute that we need to measure. And because of the power electronic filtering systems, we have some resonances in the network, which is different than old technology. And those can affect the reliability, robustness, and quality of the grid and infrastructure, especially cables and transformers. But having said that, I do believe it's important to monitor and analyze high-frequency harmonics above 2 kilohertz. The main point is that when we are talking about harmonics, we are not talking about below 2 kilohertz. We are talking about high frequency, which is one of the emerging issues. And I believe those systems are important to be analyzed in terms of the simulation and analysis, and we need to work with utility and power companies to manage the level of the harmonics. Thank you very much for your attention, and I'm happy to answer if there is any question.
Thank you, Professor Zare, for your insights. I'd like to welcome our second speaker, Ilya Dr. Ilya Budovsky. Dr. Budovsky heads the electricity section at the National Measurement Institute of Australia. He is responsible for the development and dissemination of Australian physical standards of measurement for electricity and time quantities. Many of these standards resulted from his research. He also leads the Energy Efficiency Focus Group of the Asia Pacific Metrology Program, a regional grouping of national metrology institutes. Please welcome Dr. Ilya Budovsky.
Thank you very much for the introduction, and it's my pleasure to take part today and introduce the system that we are developing at the National Measurement Institute to calibrate high voltage and high current devices at frequencies up to 10 kilohertz. Renewable sources of energy, energy efficient appliances, are clearly the future of energy. And like all new technology, they come with some challenges and with some need to support them. The power electronics that interfaces the distributed energy resources to the grid works at higher and higher frequency, and that leads to growing contributions of harmonics, particularly those of high order. Now, to understand how harmonics propagate in high voltage networks and to understand how to mitigate them, we need to measure them reliably, and we need to measure them traceably so that we can relate them to international system of units and to the national standards that governments maintain. So to do that, new measurement systems and new measurement methods are necessary, and this is what I'll be talking about what we are doing at the National Measurement Institute to do that. Let me start by very quickly introducing the National Measurement Institute, where I've been working for many years. Our responsibility under the National Measurement Act is to look after the top-level measurement infrastructure for Australia. Our job is to make sure that measurements in Australia are reliable, fit for purpose, and internationally recognized. We do it through a number of activities, through policy activities and through technical activities. We also administer national trade measurement system, and we support adoption of new technologies worldwide. There are many offices, and there are many staff in the National Measurement Institute, mostly engineers and scientists. Our headquarters are in Sydney, in Linfield, and you're welcome to visit them and see how we do this work. In very simple terms, in relation to the matter of discussion here, when we measure something, we do it in terms of units, and we provide a value. We all do. And very importantly, for a traceable measurement, we need to provide an uncertainty. And the uncertainty, this result is stated in the my calibration report, and very large efforts goes into ensuring that the value and it lies within the uncertainty. Our measurements are accredited not only by NATA, the Australian laboratory accreditation provider, but also through the mutual recognition arrangement between National Metrology Institute, and our calibration capabilities can be viewed at the key comparison database that the Bureau of Weights and Measures provides. So I'm getting closer to the subject, I promise. What is traceability and calibration? It's linking everyday measurements that are important to the units of the International System of Units, SI. There is usually a pyramid of measurement or hierarchy of measurements that provides this link traceably through an unbroken chain of measurement, each associated with its own uncertainty, and through calibration, through comparison of reference. What we found when we started working on this project is that this hierarchy doesn't quite exist when it comes to numerous measurements that really matter, that occur in electrical grids. So we found that at the National Measurement institute, we had to apply our skills and our facilities and our experiences to develop measurement systems that would make it easier to credibly measure harmonics in high voltage power lines and traceably characterize them. So, what do we have to do? We are working to provide traceable calibration for voltages up to 132 kilovolts and currents up to 4,000 amps. Very importantly, and this is totally new, we will be providing this calibration on-site and with composite signals that contain a fundamental up to 132 kV and 4,000 amps, and any number of harmonics up to 10 kilohertz. So the picture here shows an on-site calibration, but that's not for this project. This is just for illustration. So what we want to do is we want to come to where it matters with the sources that create those arbitrary distorted waveforms and a measurement system that can calibrate any instruments that are used to measure them traceably. Functionally, we can view the system that we are developing as a current harmonic calibration system and a voltage system, sharing common data acquisition and data analysis. So I'll be talking sequentially about those things. And first, about the current calibration system. After some thinking, we chose the zero flux current transformer as the main measuring unit for our system. The way the zero flux current transformer works is that essentially the magnetic core and measured current flowing through the core creates flux, which is measured by a detector winding, which creates a certain signal on the secondary winding that provides a similar and the same and flux in opposite direction, and leads to zero flux in the core, and therefore the signal of the secondary winding could be the output of the device. The advantages of these systems are they're wideband, they work on both DC and AC, and they're quite reliable and quite accurate. The disadvantage is, unlike Rogowski coil, you can't split the core. You have to put something through the core. So on this slide, you can see the two basic arrangements of the calibration system that we use. On the left is the single circuit arrangement. Here, the composite signal containing 4,000 amps and its harmonic is generated by a composite current source, and the current is applied to the reference zero flux CT and the device under test. And then the outputs of the two devices are both measured by the reference digitizer, and then the comparison and the calibration occurs. This is ideal because we can calibrate terminal time traducers. The problem is that no one, including us, can generate 4,000 amps with all required harmonics up to 10 kilohertz. We can generate 4,000 amps with a limited number of harmonics, low order harmonics up to 9th, or we can generate 200 amps with all required harmonics, and we can put more turns on the reference CT to build it up, but not to 4,000 amps. Alternatively, we've introduced the double circuit arrangement, where there's two separate circuits going through the reference current transformer and for the device under test. There's 50 hertz and a small number of its harmonics generated in one circuit, and then the harmonic currents are added in the second circuit. And of course, the 50 hertz source and the harmonic source are synchronized. And then again, both devices are measured by the digitizer. So we've relied heavily on the history of our work to provide traceability to these measurements. And that comes from calculable resistors through special current charts that we've developed. And all of this is used first to calibrate a 200 amp zero flux transformer. So this slide gives just a little bit more detail on some of the standards, but in the NMI current shunts, you can see the shunt is a parallel combination of a number of resistors and special arrangement that ensures the non-inductive nature of it. You can see the frequency response of these shunts with frequency, the horizontal axis is in kilohertz and the vertical axis is in. So on this scale, 1% is in the stratosphere. So we're quite all right with accuracy. So we've used these shunts to first calibrate the 200 ampere reference CT, and then we do a simple comparison with the 4000 amp CT, putting 5 turns on the 4000 amp CT to make the current equivalent to 1000 amps. Now, the idea here is to calibrate the reference CT this simple way, and then using the double circuit to prove that the double circuit actually work, and then to calibrate it using separate references. That's shown on this picture, and you can see here that we've chosen quite heavy combination of harmonics, 20% up to 9th, 10% up to 23rd, and 2% up to the 200 harmonics. We've used a particular IEC standard to choose these values. The next slide shows the system. It shows the system in its physical configuration. You can see arbitrary waveform generators that produce synchronized signals. You can see the fundamental source, the amplifier, and the transformer, and then the zero flux transformer and the transconductance amplifier that provides the harmonic source, and also the digitizer and that does the measurement. So the objective is, well, to ensure or to verify that a simple measurement and the double circuit measurement give results that agree. I'm sharing results that didn't quite agree as first. Well, if you 1.1%, then probably it's okay. But we wanted to understand where some small disagreement has arisen between the two measurements, and you can see the phase, the in phase, and the quadrature component. And I'm glad to report that we found the problem. The problem was that the 50 hertz signal was not pure, so it did contain harmonics that could not be measured by the reference CT, obviously. So what we have done then is we've calibrated the reference that was used for 50 hertz measurement. We've calibrated it for harmonics, and then we could adequately measure all of them. And actually, in the later design, we thought, all right, why don't we actually use the 50 hertz source to produce some harmonics? And that was very successful. So it now produces harmonics up to the 9th. All of this, as shown here, all of this led to very, very nice agreement between the two methods. And it says that both of them work, and we can calibrate the reference separately. We also reduced the standard deviation or repeatability to around 0.01% or about 0.03 centiradians, which is more than enough for this job. And this picture shows this improved arrangement. The final piece of work for the current system is to test its linearity. We've done it by doing a linearity test in a double circuit arrangement, and the results are presented here. We did it for some groups of harmonics, and the results are excellent up to the 44th harmonics, and they are acceptable for all other harmonics, but we're working on making them excellent as well. So this is more or less all about the current system. Let us now go to the high voltage system. Here again, we need to generate 50 hertz, in this case 92 kilovolts for 132 kV system, and harmonics synchronized with the fundamental. Luckily for voltage, we only need 1 kilovolt in harmonics. And again, we are working with a bandwidth of 10 kilohertz, and our target uncertainty is 0.1%, even though we want to do much better. So here's the schematic of the system. Again, we have two synchronized sources, a 50 hertz source and a harmonic source up 10 kilohertz. The 50 hertz source feeds a step-up transformer that produces the high voltage, and the harmonic generator feeds a wideband amplifier. And then the trick here is that the low of the step-up transformer, as you can see, is not connected to the ground. It's connected to the high output of the wideband amplifier. So it's floating by a kilovolt. So the harmonics and the 50 hertz are summed together. And to help this, we have a compensation capacitor of 10 times the value of the divider that loads the system across the 50 hertz transformer. That's just to lower its output impedance. Now, on the reference side, we have an SF6 compressed gas capacitor and a multi-layered ceramic capacitor forming a capacitive divider. And a 24-bit digitizer is measuring the output of the divider and the output of the transformer under test. So here's a frequency response, the first frequency response of the reference divider. You can see its voltage scale factor and the phase shift were measured up to 10 kilohertz, and we can see about 0.05% frequency response, but we can correct for that, and we are looking just where it comes from. We've looked at we've done a linearity test where we've changed the amplitudes of harmonics, and we're getting very reasonable results for the linearity, both in phase and quadrature, as you can see. And then, most importantly, we've done all the previous tests were at single frequency. What we've done is we've generated the composite signals with a number of harmonics between 2.5 and 10 kilohertz, and added up to 3 kilovolts of fundamental to it to see if there's been any changes. And you can see the changes are really minimal, both for in-phase and quadrature component. We are about to start the traceability measurement for this, and there's quite a long chain of measurement going from thermal transfer standards and going through from our other existing standards. There's just a couple of details here. So first, from thermal standards, we calibrate our 200 kilohertz reference divider that has, as you can see from the graph below, absolutely negligible AC/DC difference and phase performance up to, well, in this case, 50 kilohertz, given that the scale is microvolts per volts. And then at frequencies up to kilohertz, we can use the NMI inductive voltage divider for 1 kilovolt, which is by far the world's most accurate transformer of this kind with an uncertainty of 0.1 part per billion. And we are building a dedicated resistive 1 kilovolt resistive divider to calibrate the capacitive divider. Finally, I would like to finish quickly about talking about how we provide traceability to the measurements, to the digitizers. And in one word, that comes from quantum effect, such as the Josephson effect. You know that the Josephson effect occurs in the Josephson junction, which is a weak link between two superconductors. And the important thing is that the voltage that develops across the the Josephson junction, is proportional to the frequency of its irradiation, which we know very well. Unfortunately, this voltage for one junction is rather small for practical frequencies, so we use arrays of junctions, tens or sometimes hundreds of thousands of them. And as you can see here, for DC, over the decades, Josephson standards have provided uncertainties that are many, many, many orders of magnitude lower than those of artifact standards. There are two possibilities for AC. We can generate what's called a stepwise approximation of the AC standard, of the AC voltage. The beauty here is that the quantized, the horizontal parts of this staircase at the top of this slide are flat and quantized to parts in 10 to the 10th, but there's transients. There is now another way, which is called the Josephson arbitrary waveform synthesizer, where the frequency comes continuous source, but from a string of pulses at 15 terahertz or 15 gigahertz frequency usually. And then you can put a code into those pulses as shown here. So this is a code for the sine wave. And if every pulse, if the array is quantized, gives a finite with a quantum defined quantum of voltage. So this is the schematic of the Josephson waveform synthesizer that we use at NMI. We have a continuous wave generator feeding this ternary pattern generator, and that feeds two arrays, or four arrays actually, each at 1200 junctions. And this can provide any arbitrary waveform known to the nth degree. This is how the setup looks, and you can see the electronics, but you can also see the cryostat, because the Josephson effect occurs at cryogenic temperatures. This is one of the results. We've shown it before. It's called the quantum NMI logo. This is a spectrum of a fundamental, and 43 its harmonics, and we've chosen the amplitudes of these harmonics just so that the spectrum reads NMI, and you can see on the right, the bottom right, this signal in the time domain. Of course, this quantum NMI logo is not useful by its own right, but what's useful is that we can create any waveforms, such as the ones that we would use for this project. And here's just an example of a waveform that is very typical for light-emitting diodes and solid-state lights. And just by the way, this work was awarded by the IEEE in Instrumentation and Measurement Society, a technical award for 2021. So these quantum standards we will use to calibrate, or we're already using to calibrate, the digitizers that are used in this system. So they are traceable to quantum standards and to essentially signals with unlimited accuracy. So in summary, we are developing an on-site calibration system for high voltage and high current transducers for transmission level voltages and currents. Very importantly, we will calibrate these current and voltage measuring devices with arbitrary waveforms. We can come on site and we can generate the fundamental and the harmonic of any kind that would represent what can be present in real situation on real power lines in the real grid. Our target uncertainty is 0.1% for the ratio and 0.1 centiradian for phase. We are well ahead of that for current, and we are working to achieve that, and hopefully much better than that in voltage. Finally, just to mention that this work is part of a global innovation linkage project. We're working with the team of academia and international partners, And this picture shows the kickoff meeting that occurred at NMI to start the project. And it's absolutely delightful to see how government and academia and industry and overseas partners all work together to achieve something that's really important to support renewable energy. And finally, please don't hesitate to contact us, and please send us messages, call us. You are welcome to visit us. And last but not least, thanks go to the team that has been working with me, to all the wonderful people who have been working on this project and contributed to different parts of it. Without their contribution, the project wouldn't happen.
Thank you, Dr. Budovsky, for your incredible insights into the complexities of measuring higher frequencies. It is clearly a significant problem that we've got coming forward into the grid when we look at the numbers of different types of inverters that Professor Zare was alluding to, the interactions that we might see in the future, and the complexities of trying to ensure that we avoid resonance in the system certainly go a step further than anything I had ever contemplated in the past. Nice to see, though, that we can argue strongly to maintain the fundamental frequency at 50 so that we can actually try to hold our system in a manner that we can perform reasonable measurements. I would like to remind everybody that our speakers are now going to come together with us to take questions. And if you'd like to submit a question, please do so via Slido. The link and the code are in the description box below. And please ensure you provide your name and who the question is for. And we did receive some questions on registrations, so we will start with that. I would like to ask a question of Professor Zare. I just would like to understand whether you've undertaken any analysis on the grid forming inverters that are now being used to overcome some of the limitations of the current source inverters that are mainly grid following, and whether or not this makes a difference in some of the analysis that you've been undertaking.
Yeah, thank you very much for asking that question. In fact, when we are talking about grid following or grid forming, we are talking about the power electronic technology connected to the network. So having said that, in terms of controlling the power, it doesn't matter whether you have, in terms of harmonic emission, it doesn't matter whether you have grid forming or grid following. It mainly depends on how you design your converters. And if you look at that type of technology, we are talking about type 3 and type 4 from my presentation, that you have mainly three-phase systems because of the high power, and you end up with LCL filter. So in that case, how you synchronize system, how you can quickly basically control the system in terms of any large disturbances coming to the system, and how your control system is designed in such a way that it can filter background harmonics. These are the issues that we can basically manage harmonics and resonances in the network.
Great, thank you. And to Dr. Budovsky, the extremely small emission limit allocations that appear to be provided to connecting generators, would you like to comment on the accuracy of instruments and also the practice of allocating very, very small emission limits to generators that they have to comply with?
Indeed, Kate, the measurement always needs to be fit for purpose. There is no second answer to it. We measure less accurately than we need, we lose the benefit and may not be able to use the results. We measure more accurately, that leads to perhaps unnecessary costs. So clearly, we need to ensure that the measurement requirements are set up in a very sensible way. It's clearly not possible to measure more accurately than the instruments can provide. Likewise, the instruments cannot be any more accurate than the high-level measurement systems that support them. So hopefully my presentation went into some small way in showing how we build this foundation, how we first make the standards, the reference systems that hopefully will allow future measurements to be traceable and come with low uncertainty.
Great, thank you. We've got a few questions that have come in from the floor, and I've got a few here that are listed. I'm going to ask Professor Zare, can the DNSPs provide the network impedance as a function of frequency at the connection point? That's from Henk.
We have had some work with our European colleagues when we try to analyze the harmonic emission above 2 kilohertz. It has been some measurement managed by EDF that I was involved, and we have measured the impedance from 2 to 9 kilohertz. And in fact, yes, there are different methods that they measure, because without that one, it's very hard to look at the compatibility level when we define harmonics. So yes, there are some ways that they are measuring, and I'm sure that this is important for harmonic measurement and harmonic estimation in the network. And we are trying to work with utility companies to make sure that if there is any specific sectors or feeders that they concern, we can do some measurement based on injecting the signal and measuring that one.
Right, so that would mean that the system frequency impedance, the harmonic impedances for a particular view backwards into the network could be provided for those very high frequency orders.
Up to 9 kilohertz, I'm aware of that measurement, and we have realized that when there were different sectors in distribution network, that they try to look at the average, we have realized that depending on whether it's commercial or residential or industrial, there are different impedances. But as far as I know, the measurement was done on up to 9 kilohertz. And there are some measurements that above 9 kilohertz doesn't give a big picture because of the capacitive coupling. The network depends on where you measure.
Yeah, could you comment then on with very high frequency, is there any work been done on how far they propagate through the system? Because from our wave theory, we would think that a high frequency would not travel as far unless it's resonating, I suppose, or exciting something in the system. So I'm just wondering if you could comment on what we would normally expect with respect to distance, or how far you would expect high frequency to propagate.
Yes, that's a good question. If you look at one of my slides, I clearly measure and explain that one solar inverter with a switching frequency around 20 kilohertz, the harmonic couldn't pass through the transformer. And that was a specific case because at the point of common coupling, we had residential sector connected to the same point. So when you are talking about a residential area, in fact, we are talking about lots of home appliances which has internal filter, and internal filters are mainly based on capacitive. So when we are talking about capacitive coupling means at high frequency, low impedance. So that's why, depending on whether we're talking about a combination of residential and industrial, so in that case, more or less immunity issue, that harmonic from one unit can be circulated to another. But generally speaking, in the distribution network, medium voltage, low voltage, harmonics below 20 kilohertz are important. And I have to say that resonances are mainly below 9 kilohertz, because when you design your converter at the switching frequency of 20 kilohertz, your filter is tuned at 1/3 of that switching frequency. So that's why the main concern that we have had discussions with industry and some research partners, that frequency below 9 kilohertz are important in terms of the level of the harmonics and in terms of the resonances can happen in the network.
And so you would expect to see for that approximately 9 kilohertz in LV networks, you're saying. So that would be single phase issues for residents. Is that the concern?
Is a combination of single phase and three phase, and in fact depends on medium voltage or low voltage. One of the test results, measurement result that I shared for that significant high current in solar farm, in fact, that specific feeder and wind solar farm was connected directly to the medium voltage through the transformer without having any residential sector connected. So that's why in that case, the effect of high frequency or the possibility that high frequency can be propagated to the medium voltage is significant because there is no any other low impedances and the harmonic can pass through the transformer. And this is one option. But in terms of residential, normally switching devices in residential sectors for home appliances has a high frequency above 24 kilohertz. When we design power converters, when we normally increase the switching frequency above 24 kilohertz because of the audible noise. So that's why we design a pump that you should really touch the unit to make sure that it operates. It was completely silent. So that's the reason that in residential sector, the switching frequency is very high, but we have many power converter designed for motor drives that the switching frequency is 3 kilohertz, 5 kilohertz. Why? Because the environment for industrial sector, the noise is not one of the factors in the design.
Thank you. Thank you. I will revert to some of the questions that have come in then. There's one again for Professor Zare. I understand that some of the harmonics produced by VSDs travel down the earth connection, and in some cases it is thought that these harmonics are interfering with communications on cables through the shield being connected to earth. Is this normal, and what can be done to reduce the effects? And that's from Matthew.
That's a good question, because see, when we have motor drive VSD or variable speed drive, normally one of the problems in those applications are common mode current, and that's because of the switching pattern connected to AC machines. So therefore, to mitigate that one, they put the specific common mode voltage filters. So in that case, the leakage current definitely can pass through the system, but we have some standard for RCD that the leakage current should be below a limit. But having said that, those leakage current pass through the network should be managed based on the CISPR standard. So that's why we have a different types of EMI filters, electromagnetic interference. But I have to say that when you install those equipment, you have to make sure that your motor drive is supplied with a specific EMI filter that you need. And that's why some of the motor drive manufacturers sell the EMI filter with the unit, or you need to select based on how you can manage it. But in that case, the common mode current pass through the capacitor through the shielding or protective earth is mainly has two components. One is the low frequency, which is very low because mainly is the 50 hertz coming from the grid, and that capacitor has a high impedance at low frequency. The other one is that it might basically create some high frequency from other devices through the capacitor. So that's the main reason that we have mentioned that electromagnetic interferences and high frequency interferences has been and have been reported in many products. And that's why some of those one are above 9 kilohertz, and some of those are mainly EMI issues that has been very well established. But I have to say that if you have some interferences, based on my experience, it is below 150 kilohertz, because CISPR standard can be applied to some of the equipment. Ilya can correct me that, for example, for home appliances and lighting devices, we have the standard, but in the near future is going to be standard to cover all the frequency range from 50 up to 30 megahertz.
Dr. Budowski, I've got a question which I'm going to throw in here because I'm aware of your work is up to 132 kV. Once we get above 66 kV in the power system, we're often using a CVT, a voltage, a capacitive voltage transformer. And in order to measure the harmonics, we often have to fit a reverse filter onto that CVT to be able to measure it. Is there any work in NMI around what that does to the impact on the harmonic, the accuracy of the harmonic measurements, given that you're replicating the harmonics via a reverse filter on that CVT?
Thank you for your question, Kate. Well, we also use capacitive dividers for measuring harmonics, and they're proving to be very, very wide band devices. Our work is mostly concentrating on the on building up the voltage scale from lower voltages and from higher frequencies to ensure that our dividers are okay. We haven't done any specific research on the influence of the CVT on them. However, it's not very clear why would you necessarily do it for a measurement device.
Okay, thank you. Right, we have got one here about the influence of harmonics from solar PV inverters. Can they cause, can the harmonics from a solar PV inverter cause a smart meter to significantly overread power consumption? Professor Zare.
Yes, as I mentioned, when depending on how you design your smart meters, and that technology is depending on your signal processing methods. I have to say that I did some measurement in a lab, not only in on lab, in even different labs, manufacturing labs, that we have realized that some of the power quality meters, very high-end technology, we had some problems because of the measurement was based on your reference signal, which was at 50 hertz. So therefore, yes, the answer is yes. It can affect the meter and it can affect the voltage and current that you measure. And these are some of the challenges that some of the power quality meters are working on.
Right. Sort of highlights to us the importance of the fundamental system frequency, which quite often gets sacrificed in our illustrious market at this point in time. I'm scrolling down to find out another one. Oh, there's a question here, which is a good question. Can Professor Zare please explain the term immunity?
Yes, immunity and emission are immunity and emissions are two common words and things happening in electromagnetic interferences. So when we are talking about immunity, means that the ability of the device which can keep operating without any problem in an electromagnetic environment. So electromagnetic environment can be our power system, or it can be in any industrial network. So when a device is connected to a network, for example, if you're talking about our computers or TV systems, we expect that the system can operate based on the fact that if we have some other noisy devices connected to the network, we don't get any interference. And immunity has based on the radiated and conducted. Conducted means through the cable, which means that the noise can be propagated to the power grid and then back to the device through the internal filters. So that's why when you design a filter based on two different concepts. One is that the emission, you make sure that your device doesn't generate significant harmonics back to the grid. And the immunity filter, which is normally capacitors that we put because it's a low impedance, to make sure that the high frequency noise or disturbances coming to the network, the device can protect the control system. So normally we have two types of immunity issues. That one is very destructive, that if you have lightning coming and if your system is not designed, the electronic part can be damaged. The other one is the disturbing, that some of the high frequency can disturb the control system, reset the control system, and these are non-destructive.
Thank you. Thank you. There's a question here on the standards, and it might be for either. I think it might be, again, for Professor Zare. Australian Grid Code draws reference to the ASNZS 61000.3.6, and I think it actually refers to 2001, probably, in the rules. It should be 2012. Regarding harmonic compliance, which considers up to the 50th order. What is the framework that we should really be using for above 2,500, 2,500 hertz or 2.5 kilohertz? What should we be referring to?
I can give my comment and answer, and definitely I'm sure that Ilya can add some more, because you are working in the same working group, IEC standardization. There is a very important task force that is running at the moment. We are working on the harmonic within 2 to 9 kilohertz. And once this is finalized, definitely it can be as a part of recommendation, and Australian standardization can look at that one as one of the important issues that we need to integrate. So currently we don't have any standard above 2 kilohertz, or if you have to say up to above order of 50th. But once the IEC standard, which is the only task force that I'm aware of, finalizing that harmonic from 2 to 9 kilohertz, then the Australian Standardization Committee can look at that one. Ilya, do you have any comment on it?
Yes, yes, certainly. Thank you, Firuz. So yes, as the author of the question points out, 61000.3.6 is a very important standard because it really reveals the methodology of how the limits of emission control are set. It also refers to IEC 61000-2-2 for compatibility levels. Now, as Firuz mentioned, work is going on the new revision of IEC 61000-430, the measurement methods, and that standard will bridge the frequency gap between the 2 kilohertz and 9 kilohertz, but that's really for lower voltages. We still need to work on standards that cover high voltages and very high currents and high frequencies, and that's subject to future work for IEC and Standards Australia alike.
Thank you. Thank you. There's another one here for Professor Zare. Inverters create a common mode voltage that drive a common mode current through system capacitance. Have common mode currents been investigated during resonance?
Yes. In fact, when we are talking about motor drives, if you look at power electronic systems, normally motor drives is the most important devices if you have to look at the common mode. The main reason is that the capacitive coupling from the AC machine with direct voltage stress coming from inverters creates significant high frequency current. I measure for 5 kilowatt motor drive, and the peak of the current was around 12 amps. So it shows that how significant is the spike and high frequency. So we design a filter in such a way that we can filter high frequency harmonics coming from motor drive into the grid. So therefore, in that case, I have to say that the current going to the network is significantly low. Otherwise, the device cannot pass the standard. So it's mandatory that above 150 kilohertz, we have to manage the harmonics. But the problem is that if you're going to look at harmonics below 150 kilohertz, that's a very challenging things that we are talking about at the moment. So in that case, the level of harmonics at the moment for the common mode is not significant. So it's more immunity issue that if you have two devices like battery charger A and B for the electric vehicle that I explained in my presentation, it's more how the current from one device can be propagated to the another device, affecting the normal operation of the system. But in general, I have to say that the high level of harmonics are differential mode, not common mode. But having said that, still we are working on device level how to manage it. But the disturbances happening in the network is because of the differential, not because of the common mode.
Right, thank you. There's a couple more questions coming in here for, there's a couple of questions on AC versus DC, and I think we have to recognise that that conversation probably happened 100 years ago. We've got a lot of AC equipment, so I can't see us flipping to pure DC, but it would be a nice thing if it was possible in some circumstances. There's a question here from Stephen. Can you measure, and this one might be for Dr. Budowski, can you measure direction of flow of harmonics to identify the source?
Oh, excellent question, Stephen. Yes, the direction of flow can be measured by measuring the phase angle between the voltage and current. So if you generate harmonics, then this phase angle will be closer to zero, and the power will be positive. If you generate harmonics, the power will be negative of these particular harmonic components, and if you absorb harmonics, that power will be positive. So you can do that, and it's a very complex technical problem. So thank you for asking.
Good. Yes, it's an interesting thing when the rules quite often consider that we're always emitting, yet in some cases you're actually attenuating and absorbing, and it's well worthwhile doing those measurements to understand whether it's your problem or not. And here's one for, and it hasn't allocated to either of them, so you can choose who wants to answer. For off-grid residential sites, we are getting requests to connect EV chargers. How could we detect harmonic issues between the battery, inverter, and EV in the field?
Yes, if you're talking about microgrid, or if you're talking about more or less a smaller scale network, having said that, the power electronic system connected to the network is more or less based on power electronic switching devices. And we have realized that when we connect power electronic to the rural area or to the weak grid, if the background harmonic is significant, some of the inverters have a problem. So the technology for battery charger and the technology for solar inverter is almost similar, because your source is DC, either for PV or for battery, and the only difference is that in the battery system is a bidirectional power flow, and in the solar inverter is unidirectional, but that technology in terms of power electronic is the same. So in terms of harmonic in that area is more or less depending on how you generate and what sort of device you use that one. But I have to say that the background harmonic, the grid impedance, and any large disturbances coming from load change or severe voltage change can affect the normal operation of your grid connected inverters. So if your battery charger or electric vehicle connected to the network that you have significant resonances or variation in the voltage, then you have a problem in terms of the normal operating mode of the converter, because these are not designed in such a way that you have significant disturbances.
Thank you. I momentarily dropped out there, and I hope I caught back up again. I think we're getting towards the end of our half an hour on questions, but there's one more question here which I would love Dr. Budowski to respond to. Can the 0.1% of harmonic voltage for each harmonic order, I think it should read, be measured? And I suppose this comes down to a number of areas where we're talking about the instruments that you're connected to.
Yes, the answer is yes, absolutely. What we do is we generate a composite signal that contains a fundamental, say, 80 kilovolts or something, and 100 different harmonics up to 10 kilohertz, and we can measure each of those harmonics in the composite, dirty signal to the uncertainty of 0.1% of the fundamental. So yes. And hopefully that will give rise to high voltage and high current instruments that can measure this. I must say that the frequency range at lower voltages and lower currents, it's much higher, it's kilohertz, and the uncertainties are again maybe an order of magnitude smaller. So the difficulty is really the high voltage end and the high current end, because we've long ago achieved much higher accuracies at lower voltages and lower currents.
Yeah, would that depend? I mean, I think in the field, when we talk about the high voltage system, wouldn't that also depend on the accuracy of the CTs and the VTs to which you're connected, as to whether in fact you can achieve the level of measurement necessary to identify that? And it might be 0.1 or 0.01 sometimes that they're asking for.
Yes. Yeah. I think this is a great point, Kate. It almost entirely depends on the accuracy of CTs and VTs. So the good news, someone asked about how to calibrate things. So it works very well to separate the transducers, in this case the CTs and VTs, and the lower voltage digitizers or power analyzers. So the measurement traceability for those is well established, and the accuracy for those can be achieved much better than for high voltage transformers. But yes, the novelty here and the technical difficulty here is how to actually calibrate CTs and VTs, and hopefully we're getting there.
Right, thank you. I think we're at the end of our session. I think that's all we have time for today, because we've just gone past the 2:30. So I'd like to ask everyone just to join me in thanking Professor Firuz Zare and Dr. Ilya Budowski for their time and insights that they've shared today. I certainly feel that I've learnt quite a bit more about what's going on in the power electronic space, and I can see going forward into our future where we don't really have fast control over the different types of inverters that are being offered on our market, and the rate at which we are going to head into electric vehicles and other various power, battery storage and other converter systems on our network. We're going to be confronted with a number of these issues. So I'd like to thank Engineers Australia's industry partner, Queensland University of Technology, for making our webinar possible. We'd appreciate your feedback on the program today and help us to improve and plan future sessions. Please complete the short feedback form, which is linked in the description box below. And thank you again for joining us, and we hope to see you at the next webinar.